The top rating chart is very important. It indicates the maximum milliampere. Each machine comes with its own top rating chart. This top rating chart shows the relationship between the exposure time in seconds and the kilovolt. On this rating chart, there are values for maximum milliampere. For example, if I set 100 kilovolt and I want to set my exposure time to 0.1 seconds, can I use 100 kilovolt with an exposure time of 0.1 seconds? What is the maximum milliampere I can use? It is 150 milliampere. The milliampere that I can provide with a certain kilovolt value is clarified through this curve, which shows you the milliampere values that you can use for this exposure time with the specified kilovolt value. This is useful, for example, when you are looking to purchase any machine. You can check the top rating chart for that machine. You might say, for instance, that I will set the exposure time to a certain duration for a specific examination, which could take 10 seconds, 20 seconds, or whatever. Now, can I apply 100 kilovolt with, say, 300 milliampere for 30 seconds or not? Because with some machines, when you set high parameters, like 100 kilovolt and a high milliampere, it might tell you that you cannot perform that scan in 10 seconds or 20 seconds. You might be limited to, for example, 5 seconds and cannot exceed that. In this case, you can almost determine the limits of what is possible. The MHU refers to whether you are buying a 3.5 MHU or a 5 MHU. The changes always occur in CT machines, where you might be offered a 3.5 machine, and you find that the price difference is significant. The difference in cost is high, and indeed, in application, work, and scanning, it makes a huge difference to perform a case with a 5 mega heat unit or an 8 mega heat unit compared to using a 3.5. You will notice that you might not be able to complete the scan. For example, some machines can take around 30 to 40 seconds. Especially with a Toshiba device, those 40 seconds are a lot, because to achieve, for instance, 250 milliampere with 120 kilovolt in those 40 seconds, the machine may not accept it and will tell you to reduce the parameters. You won't discover this until after you have actually purchased the machine.
Exactly.
You mentioned that it can be done, for example, in 40 seconds, and the patient cannot move. If I operate, for instance, for those 40 seconds, you don't need to hold your breath after the area of the diaphragm. The patient can breathe normally. For example, in a scan, you tell them to hold their breath and then breathe normally. From my perspective, in the area below the diaphragm, you need it to be stable, nothing more than that. In lower limb angiography, the technique for lower limb angiography, for example, on a 16 slice or 16 row CT machine, is done how? It is taken on the Toshiba Activion 16 row detector. The old one was done in about 40 seconds. But when they increased the table speed a bit, it was done in about 25 seconds. Now there are two machines from Toshiba. One is called Alexion. This machine has a tube of 3.5 MHU, and the tube and table speed are low, so its scan time is long. So what happens is that the technician comes, and while working at the area of the pelvis, he tells the patient to breathe normally. The patient is then stabilized, for example, at the leg area, and the examination continues normally. For instance, if you are conducting a triphasic scan, the triphasic here involves moving through different phases, such as giving a scan without contrast, followed by an arterial phase, then a portal phase, or a portal venous phase, and then a delayed phase. There are several scans involved, and you send them for further analysis. So, the scan time here, or the exposure time, doesn't allow for cooling down, for example, in 10 seconds, or maybe in 5 seconds. So this might suggest reducing parameters so you can take all these scans back to back without the machine needing time to cool down. It doesn't necessarily have to be lower limb angiography. It could be portography or trivisic, and this is straightforward. This is a narrative all about the CT tomography machine, which is considered by many experts to be the most hazardous and potentially risky aspect of all these stories in the field of medical imaging. The CT, as you all know, is currently highly sophisticated and cutting edge in terms of technology, and some diagnostic procedures, like the well-known and extensively studied triphysics examination, can reach up to 90 millisieverts of absorbed radiation dose for the patient, which is a significant amount, while the maximum permissible limit for medical personnel and staff who are regularly exposed to radiation is 20 millisieverts per year as per international safety standards. So, a patient coming in for a CT triphysics examination could receive 90 millisieverts. Now, if I talk about the CT machine, if you perform a detailed cardiac examination procedure, like the intricate and complex cardiac angiography procedure, which involves detailed imaging, you are dealing with an 8 mega heat unit tube. The technical engineer or specialist responsible for the operation and maintenance of the machine won't discuss this with you. He won't mention the comprehensive tube rating chart, which provides detailed specifications. I want to tell you that if you request this specific information from him, he will likely not provide it. I am confident because I requested it from Siemens engineers and GE, but unfortunately, no one is providing it. If you are working with what you know about the mega heat unit, for example, I would say that the minimum we consider is 5 mega heat units if we are talking about angiography and triphysics examination. If you want the machine to be operational, meaning efficient, and there is not much cooling, then 3.5 mega heat units is not sufficient. You should expect that you will need cooling down, and it will require a cooling system. Are you okay, Dr. Hani? I'm fine, but I have some doubts. If I go out, I'll open the center and let you know. And I'll open it with you, sir. This will enlighten us. I'll buy the devices for you. The topic of the tube rating chart is important because it tells you what the maximum milliampere and maximum kV are for a specific time. If you increase the milliampere value, for example, if I want to work with 200 milliampere, it will tell you the kV you can work with up to, say, 80 kV. You can't exceed that because the machine's heat capacity won't allow it. If you want to increase the kV, you must reduce the milliampere. If you want to work with a higher kV again, you need to lower the milliampere. You see the curve? Imagine with me. This section allows you to increase the kV, but at the same time, it will decrease the milliampere or vice versa. This is also related to the fact that if you find a slight change here, you will see that the focal spot size here is 0.6 meter T, and the focal spot size here is also 0.6 mm, and the focal spot size here is measured in millimeters. So, both have the same focal spot size, but here, what is the rotation limit? 3400? Here it is 1000. Does the 1000 provide better cooling or not? Better cooling, the higher the rotation speed, the better you can achieve cooling during that time, resulting in better heat dissipation and good power loading for you. This means that at the same kV, you can operate with a higher milliampere, like 400 milliampere, because your RPM is high. So, even with the same focal spot size, the higher rotation allows you to work effectively and efficiently. Understanding these specifications will help you choose the machine confidently, knowing that you can operate it effectively. Here, for example, what is your focal spot size? It increased to how much? 1 millimeter. So when you compare 0.6 millimeters to 1 millimeter, you find that you can operate at 75 kilovolt with 500 milliampere, the same rotation, but the only thing that increased is the focal spot size. Now, when the focal spot size is in this case, what will happen? The heat distribution will be better because the area exposed to the electron beam has increased. In this case, there will be better heat loss, and you will have good power loading, allowing you to increase the milliampere value. Now, when you compare 3400 RPM with 1000 RPM? Is 3400 RPM compared to 10,000 RPM? You find that you can work with 1000 milliampere, and this is compared to 3000 RPM with the same focal spot size, but the main difference here is 3400 and here is 1000 RPM, which is the rotating speed. All right, doctors, you separated from me. So the parameter at the end, the graph below, will definitely increase the efficiency. Increasing the parameter will definitely enhance the efficiency. It's good for cooling, but it will increase the efficiency. This is sure. But as someone working on the machine, what matters to you is the application you want. Let me say, there are two schools of thought. Today, for example, I want to work on a scan like a cardiac exam. I have no problem with the patients. I'm speaking in terms of market language. They might say that the patient dose is not an issue for me. The important thing is to increase the parameters. When we talk about dose optimization, the kV, milliampere, and their relationship come into play. There are other parameters. I have 5 parameters in computed tomography that affect the patient dose: kV, milliampere, rotation time, pitch factor, and something called beam collimation. These are the 5 main factors that affect the patient dose. When I work, it's not just about kV and milliampere. I can significantly reduce the time of exposure by increasing table speed or decreasing rotation time, which results in a shorter scan time, leading to a lower patient dose compared to other methods. However, this is not absolute. It depends on the type of exam and the version you are working on. Yes, sure, doctor. As I mentioned, the maximum available power decreases, meaning that the highest power you can provide has a lower value based on certain factors. If you increase the exposure time or reduce the focal spot size, then the power or the values of the kilovolt and milliampere that you will use must decrease. The disk diameter of the anode matters. The larger the diameter of the rotating anode disk, the more heat dissipation occurs. While you are diligently working, you consistently emphasize the impressive power and capabilities of your chosen device. This device is known for its exceptional performance and efficiency, making it an indispensable tool in your daily tasks. You trust in its ability to enhance productivity and support your work, ensuring you achieve your goals effectively. Decreasing effective focal zoom size and the actual focal zoom size decreases effective focal spot size. So what does this mean? It means that if you have a small size, it also indicates that it is small. And if the effective focal spot size is the same, this means that the effective focal spot size is also the same. I have a doctor, which means it's the same indication. It's the same idea, you understand? I mean, when you tell me today to think about the focal spot size, it will be small. This is also an indication that your actual focal spot size is small, not large. Okay, but we remove the option for the anode angle. This also depends on the type of your machine. But if we say now that let's fix all the factors, and now I will reduce the focal size. So you are a user of this particular system and you have decided to reduce it, the focal spot size. What will happen to the power output of the system as a result of this change? Now, you have changed the effective focal spot size, which is a critical component in the system, but how exactly will you change it? Will you choose to reduce it further or increase it instead? Great, you decided to reduce it. So, did you increase the heat generated on the anode or not? If you reduced the maximum power output of the system, then that's the significant change you have made. This is the point I was telling you about. If you use milliampere, you won't be able to use the maximum kV with both milliampere together. So you have to increase one and decrease the other to reach the idea that the machine can give you the scan you want. As we were discussing in this curve, when the kV is low, your milliampere is high. If you want to increase the kV, you will find that your milliampere must decrease for your machine to work. This applies to any machine, but of course the matter is relative depending on the focal spot size, the rotation of the anode, and the other factors we were just talking about. Here we have the anode cooling chart. For example, if this happens, you can request it from the machine itself. The machine needs to reach zero. This zero area requires complete cooling. For instance, if I had a value that needs to reach this point, how long does it take to get to its zero? From this curve, you can see that it takes about a certain time, which is approximately the time needed. So, to say that this cooling gives you an indication of the time the machine needs to reach the state or the optimum state to provide a new exposure. Now, does it have to reach zero? No, it doesn't have to, but it depends on the scan you will perform afterward. For example, if I'm going to do a scan afterward, it might increase it by about 10,000 megahertz, and you will notice that this is usually the case. You need to carefully lower it to the point where there is sufficient space or a noticeable gap, so that when I increase the exposure to approximately 30,000 megahertz from the new scan, it does not exceed the anode capacity or the maximum temperature of the X-ray tube. There are sophisticated electronic circuits inside the X-ray tube that will notify you if you exceed that limit based on the specific parameters you are using, telling you to wait for about 5 to 10 minutes or until it stabilizes. For example, if you want to perform a scan, you can increase it, but your absolute maximum is 30,000, which is the maximum limit. It will allow you to operate between 90 to 130, so there are about 40,000 heat units that you can work with, and you cannot exceed that. If you want to conduct a tri-physics examination, it will require significantly higher heat units, so you need to wait longer for the cooling to drop to a lower value before you can perform your examination. Additionally, always ensure that the equipment is functioning optimally. Doctor's mask. Is it the mask we designed correctly? Maybe we take a 10-minute break, or we can stand and continue with the book. If we consider this part, what remains is just the information about the half-value layer, which Dr. Hani was even asking about, and its relation to attenuation. After that, we can discuss screen film radiography and digital radiography. If we want to install the information about the health value layer here, it's not difficult. Its relation is just with kilovolts, its relation to energy, and its relation to the type of beam, whether it is a polyenergetic or monoenergetic beam. So we can talk about it tomorrow as a start, and then we can move on to screen film radiography. We will try, God willing, to finish screen film and then get into digital imaging. No problem, no problem. All right, we have been at this for about 2.5 hours, so I think you can take a break, and I can too. All right, doctors, let's go. Any questions? Go ahead. God protect you. If the Google form allows, sometimes the question can have more than one answer, but it has to be one point only. So for example, if I say I am in case A, B, and C, then I am in case 3, meaning A, B, and C.